Hi guys, how are you? I hope you're doing well. So today I'm going to talk about section 14.3, that's partial derivatives. So we're going to learn how to compute the derivative of function of several variables, okay? Well, so let's start with a function of two variables. So just function f, function of x and y. So we have f of xy equal to z. So again, the z, that's like the, so that's that's equal to f of xy. So we're gonna have like three axes here. So here's my x, here's my y axis, and here's my z. And so the graph of f of x, y. So here, let's say this is here. This is the graph. So this is the graph of f of xy. So the graph of f of xy, again, we said the last time, the graph of a function of two variables, it's not like a line or a twisted line. It's actually a surface. It's a space of dimension 2. So it's like a twisted plane. Okay, so the graph of f of xy, it's actually a surface. So it's two-dimensional space. It's two-dimensional space. Okay, now anyway, so let's just take a point AB. So here, let's say this is the point AB. So my x is equal to A. So here x is equal to A. And here, okay, y is equal to B. Okay. So here, y is equal to B. Okay. So what I'm gonna do, guys, I'm gonna fix, let's just fix the line. So fix y to be equal to B. So let's say fix y equal to B. Okay, so y is equal to B, that's the equation of a line. So that will be this line here. So this line here, this whole line here, this green line, the equation of this green line is y equal to B. So this is the line y equal to B, right? Now, let's take the image by the function f of this line y equal to B. So for example, here we said we have the point AB here, right? So the image by the function f, so here's, let's say this is the image of AB. So that will be f of AB, right? This is f of AB. Okay, so you take any point in this line here and you associate its height, which is given by the function f of xy, right? So for example, here you're gonna have, let's say, this point here, here, this point is gonna go somewhere here. Okay, so to each point of the line y equal to B, you associate, you have its image, right? So that will be a point. And then if you connect all these points, so if you connect all these points, you're gonna have a curve, right? So if I join all these points here, so it's gonna be a curve here. Okay, so this is the curve C here. So the curve C is the image of the line. So C, the curve C, that's the image of the line y equal to B by the function f. F of xy. Okay. So what I'm saying, guys, basically is, you have this line y equal to B. Okay. This is my line y equal to B. Here's my point AB. So let's say this is the point AB. X is A, y is B. Anyway, y is fixed here. Okay. And so the image here by the function f is going to be this, the curve C. So that will be, so the image here is going to be this curve this one here, this curve C here. So we're gonna have this is my curve C here. Right, this is my curve. This is my curve C. Okay, and let's say this is here. This is the image of, this is f of AB, right? So this is f of AB here. Okay, so guys, well, you know, this curve C, you know, if you take the slope, so the slope of the tangent line to C, so this line here, so my curve C, I'm gonna take the tangent line, so here's this line here, so this is the line L, so the line L, this is the tangent line to the curve C, passing through the point. You know, the point f of AB, so passing through f of AB here, right? Then, well, then this line L, of course, has a slope, right? So then the slope of the line L, that will be equal to the actually to the derivative or partial derivative, to the derivative of f of x, y, with respect to, so here, the y here is fixed, right? So y doesn't change, right? It doesn't vary. X changed, the value of x changed, right? But here the line y equals to b. So here, this line here, the y is fixed, is always equal to b, right? So, but the x, the value of x varies, right? So then here, this slope of this, the slope of this line L would be the derivative of f of xy with respect to x, because y is fixed, is always equal to b, so it's fixed. Okay, and that's exactly, so that's the partial derivative of the function f with respect to x, because again, because y is equal to b, so it's fixed, right? So so this slope here of the line L, so by the definition, so it's gonna be equal to, as I said, it's a partial derivative, so, or the derivative of f with respect to x. So this is the notation for a derivative of f with respect to x. So this is derivative of f with respect to x. Okay, so that will be equal to, at the point AB, okay, because we are interested in, you know, the slope of this line L, which is a tangent line to the curve, you know, to the curve C, and it passes through the point f of AB. So we are interested in the partial derivative of f with respect to x at the point AB. So by definition, that will be the limit h goes to 0. Okay, so that's just a, you know, the slope of the tangent line of f of, so here x varies, right? So here it will be, this is the point AB, right? So it will be f of a plus h b minus f of ab over h. So you see here in this definition, guys, the main thing, you see the value of y. The value of y is fixed. So y here is fixed, is always equal to b, is fixed. Okay. However, the x, so here, so we are at the x is equal to a here, and you want to compute the derivative of the function f of this function, at the point AB. And of course, the derivative is always about the behavior of the function in the neighborhood of the point. So you're gonna vary here, the values of this function f. So here you vary the variable x. So here it's a plus h, and here a, right? So you vary x, but y is fixed. Okay, so that will be the partial derivative of f with respect to x at the point AB. Okay, and of course you can do the same thing for derivative with respect to the derivative of f with respect to y. So what we can do is again, so you have this picture here. Again, this is x, here's z, this is y here. So again, you have this function f, this is my function f, graph of f of xy. So graph of this is f of xy. Okay. So we can do, again, you can take a point here, AB. So this is a point, this is point AB. So my x is equal to a is here. And this is my y equal to b. Okay. So what I'm gonna do now, I'm gonna fix x. So x is gonna be equal to a. So I'm gonna fix x. So here, this is the line x equal to a, right? Here, this is x equal to a. This is the line x equal to a. And now we can just take the image of this line by the function f. So like this point here, it goes here. This point here, it goes somewhere here. This one here, it goes, I don't know, let's say somewhere here, etc. So you have a bunch of points, and then you can just connect all these points. So that will be this curve here. So we're gonna have a different curve. So let's say I'm gonna have this curve, another curve. Okay. This is a curve C. Okay, so this curve C, it's the image of the line x equal to a. Okay, so x is fixed here, x is equal to a. So C here. Now this is the curve. So this curve C is the image. So curve C is the image of the line x equal to a by the function f. So here my point is x is fixed. So here x is fixed is equal to a. Is equal to a. X is equal to a. But the y, the variable y varies. Okay, the variable y can change. And again, the same idea here. So we're gonna have. So then the tangent line, so if you take the tangent line to the curve C at this point, f of AB at this point here. So if you take this tangent line here, probably I should use a different color. So you take this line here, which passes through this point and it's tangent to the curve C, then the partial derivative of f with respect to y at the point AB, that will be the slope of this line L here. Okay, so then partial f, partial y at the point AB, that will be the slope of the tangent line L, okay, to the curve C at the point, f of AB, or at the point AB, f of AB. okay? So by definition, you can, so by definition, here, so by definition, so partial f, partial y at the point AB, that will be equal, limit, h goes to 0. So now, you know, x is fixed. X, it's equal to a. So that will be f of a here, okay, minus f of a here, okay, and then you vary y, right? So y at the point AB. So you're gonna vary b. So here is gonna be b plus h, and here it's b over h, okay? So this is the derivative of f with respect to y at the point AB. So you see again here, the x, which is equal to a, is fixed. So x is fixed, and it's equal to a. But the value of y at b, so here b varies, right? So that's why it's called the partial derivative of f with respect to y, because x is fixed, okay? It's equal to a, so it's fixed. So in general, so this is at the point AB, but in general, so in general, a partial f, partial x, that will be, so the derivative of f with respect to x at any point xy, okay, doesn't really, it's xy is not fixed, so at any point xy, so that will be equal to the limit h goes to 0 of, so partial f, partial x is, it means that y is fixed, so x varies, so that's f of x plus h, y, minus f of x, y, over h. And again, you see guys, y here is fixed, it doesn't change, it's the same thing here, it's the same y, but the x varies, right? And partial f, partial y, so that will be limit h goes to 0 of f of x, so x is fixed, so and y varies, so y plus h minus f of x, y over h, okay? So let me just before the examples, guys, so let me just say a word about notation. So derivative of f, or partial derivative of f with respect to x. So this is, we use this notation here, partial f, partial x. So this is, so this is partial derivative, partial f, partial x. Okay, or in other words, that's the partial derivative of f with respect to x, partial derivative of f with respect to x, okay? Well, so this symbol here, this is for partial, okay? So partial f, partial x, and we can actually use, instead of using partial f, partial x, you can use this notation here with f sub x, or f index x, okay? So it's the same thing. So this is the same, it's also partial derivative of f with respect to x, okay? And the same thing for partial f, partial y. So this is partial f, partial y, or the partial derivative of f with respect to y, and it can be denoted as like f and sub y, or f index y, okay? It's the same thing. Now let's do an example. Let's say f of xy is equal x squared y. Okay, so let's just compute, for example, what will be partial f, partial x, or the derivative of f with respect to x. Okay, so then partial f, partial x, we said is supposed to be the limit h goes to 0, right? F of, so this is a partial derivative with respect to x, so y is a constant, so y is fixed, so this is x varies, so x plus hy minus f of x y over h. Okay, so So we know f of xy, right? This is f of xy. But we need to figure out what's f of x plus hy. So what will be f of x plus hy? So let's see. So f of xy is x squared y, right? So then f of x plus hy. So here, you see guys, you need to replace x, this x here, x by x plus h. So this x here is gonna be now x plus h. So that's x plus h squared times y. Okay, so this is like the circle is like parentheses, so that's like x plus h squared times y. Or if you prefer, so we can, if you expand the x plus h squared, so that will be x squared plus h squared plus 2hx times y. So that will be x squared y plus h squared y plus 2hxy. Okay, so that's f of x plus hy. Okay. So now let's compute partial f partial x. So partial f partial x. So that's limit h goes to 0. So f of x plus hy. So we said it's x squared y. So x squared y plus h squared y plus h squared y plus 2hxy plus 2hxy minus now f of xy, right? So f of xy is x squared y. So it's minus x squared y over h. So x squared y here cancel out. So that will be equal to the limit. H goes to 0, right? H squared y plus 2hxy over h. Right, so we can factor out h in the top, so this is the limit, h goes to 0, so we can factor out h here, so that will be hy plus 2xy over h. So then now h cancel out, okay, so that will be equal to limit, h goes to 0, so it's hy plus 2xy. So now just replace h by 0, so h is equal to 0, so this is h 0, so it's 0 times y plus 2xy, so it's equal to 2xy. So we see then, so partial f partial x is 2xy. Okay, and for example, so what will be partial f partial x at the point, let's say 1, 2. So that means x is equal to 1 and y is equal to 2. So we need to plug 1 and 2 in partial f partial x. So this x here is 1 and this y here is 2. So it's 2 times, so it's 2 times x is 1, so 2 times 1 times y, right, 2xy, so times y, so times 2, so that will be equal to 4. So partial f partial x at the point 1, 2 is equal to 4, which means, again, this 4 here, that's the slope of the tangent line to the curve C, which is the image of the line. So here y is fixed, so the line y is equal to 2, okay, at the point 1, 2, f of 1, 2. So this is the slope. So 4 is the slope of the tangent line to the image of the line y equal to 2. Here, because y is fixed, so y is equal to 2 by the function f at the point by f of xy at 1, 2, at the point 1, 2. F of 1, 2. Okay. So that's now an example. Of course, we can compute partial f, partial y if we want, and it's just a similar computations. But the only thing is here, instead of having x plus hy, so it's gonna be x y plus h. So for example here, so what I'm saying, guys, if you want to compute partial f partial y, So that will be limit h goes to 0. Now it's f of x y plus h, okay, minus f of x y over h. Okay, and then you do this similar computations. Okay. Now, you may ask, is there a way? So can we compute the derivative without the limit definition? Can we compute the partial derivatives without the limit definition? Okay, so the answer is yes, of course. So what we do, for example, so let's do an example, and I will explain the example with examples how to compute the partial derivatives without using the limit definition. So, for example, let's say, let me come back to the same example with the x, where is it? So my function here was x squared times y, right? So I have x squared times y. And I want to compute, let's say, partial f, partial x, partial derivative of f with respect to x, okay? So what we do here, guys, we're gonna use the general rule we know, derivatives rules we know for the functions of single variable. But what we do, because here we have two variables, right? But what we do here is that if you want to compute the derivative of f with respect to x, it means that y is fixed, right? Y is fixed. In other words, it means that y is constant. So you need to consider here y as a constant. So if you want to compute the derivative of f with respect to x, you consider y as a constant. So here, so we have, x squared times y, okay? So this is actually, this is a product of two functions, right? This is a multiplication, right? So it's a multiplication, so, if you have a function of single variable and if you have a multiplication, then you use a product rule. So I'm going to do the same here. I'm going to use a product rule. Remember, a product rule was derivative of f times g. That would be f prime g plus, so derivative of f times g is f prime g plus fg prime, right? So here, this is like my f here. This is like my g. So it's a product rule. So first, f prime. So f prime, derivative of x squared, right? So what's the derivative of x squared? That's 2x. So this is 2x times. So that's my f prime. Okay. Now, times g. So what's g? G is equal to y. But y, remember guys, y is a constant. So this is constant. Y is a constant. And so what's the, right? So f prime times g. My g is equal to y. So that's 2x times y. Plus, so here. So this is my g here. And then I have f times g prime. So f is x squared, right? That's my f. So my f is x squared times, so this is here, this is my f times, here is supposed to be g prime, right? But then y, g is y, right? But then y is a constant. Okay, because this is derivative of f with respect to x. So y is fixed, so it means that y is a constant. And what's the derivative of a constant? Derivative of a constant is just 0. So derivative of y here is just 0. Okay, because y is a constant. So that will be equal to, so again, this is because y is a constant. So that will be equal to 2xy plus x squared times 0. So it's plus 0. So partial f, partial x is just 2xy. Now, if you want to compute partial f, so again, f of xy is x squared times y, right? That's my f. I want to compute partial f, partial y this time, okay? So partial f, partial y, it means that x is fixed. And if x is fixed, it means that x is a constant. Okay. And again here, we have x squared times y. So that's a multiplication, so I have to use a product rule. So this is a multiplication. All right, so we need to use a product rule. Okay. So we use a product rule. So this is like my f here again. This is like my g. So that will be f prime first. So what's f prime? F is x squared. What's the derivative of x squared? Well, here you need to remember that x is a constant because we are deriving with respect to y. So x is a constant. And if x is a constant, x squared is also a constant. It's just some number, right? Square of a constant is also a constant. And so the derivative of a constant is 0. So that would be f prime here. It's not 2x, but it's going to be 0 because x is a constant. And so x squared would be also a constant. So f prime here is 0 times g, which is y, plus, so here y is g, plus f. So what's f? F is x squared times g prime. So g is y. What's the derivative of y? Y here, it's not a constant, right? Y is a variable. What's the derivative of y? It's like saying, what's the derivative of x? Derivative of x is 1. So derivative of y is just 1. So it's x squared times 1. So that would be equal to 0 plus x squared. And so partial f, partial y, that would be x squared. Let's do another example. So let's say now f of xy is equal to, let's say x sine of y, okay, plus y e to the x. Okay, so let's say you want to compute partial f, partial y. Okay, so here we need to keep in mind partial f, partial y, it means that x is constant. So x is a constant. So you need to think of x as a constant. Okay, so here I have, well, here's multiplication, right? Here's multiplication, and then you have a sum here, right? So what will be the derivative? I mean, remember guys, if you have a function of single variable, if you have the derivative of a sum, it's going to be equal to the sum of the derivatives. So first, I need a derivative of this here first, okay? And then plus a derivative of this one here, okay? Again, that's because derivative of a sum is the sum of the derivatives. Now, let's start with the green one here, the green term. So x times sine of y. So here, x times sine of y, it's a multiplication, right? So we're going to use a product rule. So here, a product rule. Okay. So what's the derivative of x times y? Again, this is like my f here. This is like my g. So I'm going to use the product rule. So it's f prime g plus f g prime, right? So now, what's f prime? F is x. What's the derivative of x? Well, derivative of x, again, you need to be careful. X is a constant. So if a derivative of a constant is 0, so derivative of x is 0. So that's 0 times sine of y. Plus, now f, that's x, times, what's the derivative? So g is sine of y. What's the derivative of sine of y? Okay, y here, it's not a constant, so it's a variable. So what's the derivative of sine of y? It's like saying, what's the derivative of sine of x? Sine of x, derivative of sine of x, supposed to be cosine of x. So the derivative of sine of y, it's cosine of y. So it's x times cosine of y. So that's the g prime. Plus, now let's move to the blue term here, this one here. Again, it's a multiplication, right? So again, we're gonna use the product rule. So this is like my f, this is like my g, this whole thing is my g, this is my f. So it's f prime, again, f prime g plus f g prime. So f is y. What's the derivative of y? Y here, it's not a constant because again, x is a constant, but not y. So what's the derivative of y? It's like saying derivative of x. Derivative of x is 1. So derivative of y is 1. So that will be 1 times g, which is e to the x, plus f, which is y, times the derivative of g prime. G is e to the x. So now, remember guys, x is a constant. If you have x is a constant, so e to the constant, it's also a constant. So for example, x is 2. So then you have e squared, which is, it's constant. So e to the x, it's also constant. So this is here, this thing here is a constant. The whole thing is a constant because x is a constant. So then e to the x is also constant, and derivative of constant is 0. So it's y times derivative of constant is 0. So that will be equal to, so the 0 is 0, so it's going to be x cosine of y plus 1 times e to the x, so e to the x. So then partial f, partial y is equal to x cosine y plus e to the x. Okay. So of course, guys, you need to practice a little bit. So this is just a couple of examples. You can find more examples in the lecture notes. Okay, and of course, if you have any questions, you can just send me an email. So that's how it works. So that's for the partial derivatives. Now, if you, of course, this is just for a function of two variables, but of course we can extend this partial derivatives to a function of several variables. So for example, here, a remark here, let's just make, let me just make this remark. So we can extend partial derivatives to several functions of several variables. So for example here, let's say you have a function f of x, y, z, t. Okay, so then so it's 4 variables here, and then what will be partial f, partial t? For example, derivative of f with respect to t. Well, it's a limit, h goes to 0, so it's derivative with respect to t. It means that x is it's fixed, y is fixed, and z is fixed. Only t varies here. So that will be limit f of x, y, z, t plus h, so you vary t, minus f of x, y, z, t over h, and etc, etc. So of course, if you want to compute partial f, partial t, so what you do is you consider, you consider x, y, and z as a constant. So consider x and y and z as constant. Okay, and derive with respect to t. Okay, so you consider x, y, z as a constant, and you derive with respect to t. Okay, next, guys, we can talk about higher order derivatives. Of course, so we can compute partial derivatives, but that's the first order. But then we can we can derive again with respect to x or y. So we can compute higher order derivatives. So if it exists, then we can compute. So let's say you have f of x, y, right? That's your function f. We said partial f, partial x, So that's the derivative with respect to x. And then you have f of y. That's the derivative of f with respect to y. So then so if you have f of x, derivative of f with respect to x, so then you can derive again with respect to x. So you're gonna have f of xx. So this is like you take the derivative of f with respect to x. So this is derivative with respect of f with respect to x, and you derive it. So here you derive it with respect to x again. So f of the second derivative of f with respect to x. So that's so here. So that's this is the second derivative of f. Of f with respect to x. You can do, for example, f of xy. So when you write f of xy, it means so you derive first with respect to x. So derive first with respect to x, and then y. Okay, so I have derivative of f with respect to x first. Okay, and then I'm gonna take this and I'm gonna derive it now with respect to y. So that's partial square f, partial y, partial x. Or you can you can compute fyx, which is, so we derive first with respect to y, and then, so first with respect to y, and then x. So first with respect to y, so that's partial f, partial y, and then I'm gonna derive it with respect to x. So here's second derivative of f with respect to xy. Okay. You can also compute fyy. So which is derivative of f with respect to y 2 times, right? Second derivative of f with respect to y. So this is the second derivative of f with respect to y. Okay, and of course you can do more than you can have a third order derivative. For example, f of xx. It means you derive 3 times with respect to x. You can do, so this is 3 times with respect to x. You can do xxy. So that's you derive twice with respect to x and 1 time with respect to y. You can do yx. So that it's like this is a 2 derivative. You derive twice with respect to y, and then you derive with respect to x. Okay, etc. Okay. So let's just do an example so you can see what I'm talking about here. Example. So let's say f of xy is equal to, let's just say it's x squared y cubed. Okay. So let's compute, let's say fxx, fxy, fyy, and why not fxxx. Okay. So first I need fxx, so that's the second derivative of f with respect to x, so I need to derive twice with respect to x. So first let's derive once with respect to x. So fx would be what? So this is derivative of f with respect to x, so we consider y as a constant, So here again, this is a multiplication, so I need to apply a product rule. Y is a constant, so product rule, so derivative of x squared is 2x times y cubed plus x squared times, so y is a constant, then y cubed is also constant, and derivative of constant is 0, so derivative of y cubed is 0, so that's times 0, so that's just 2x y cubed. So now if I want to do fxx, so what you do, you take the derivative of f with respect to x and you derive it again with respect to x, right? So here, this is derivative, this is a first order derivative with respect to x. So I need to derive it again with respect to x, derive it again with respect to x, okay? So that will be the second order derivative. So let's derive this again. So, sorry, so this is 2x y cubed, right? So this is, again, it's just 2 times x times y cubed. So derivative again with respect to x. So derive fx with respect to x. Okay, so fxx. So here, this is my derivative of f with respect to x. I'm going to derive it again with respect to x. So here, well, 2 is just constant, it doesn't really matter. So here I have a product again. So this is x times y cubed. So product rule, again, derivative of x would be 1. Or we can just take here instead of 2 instead of x, we're going to take 2x. So here I have this 2x here times y cubed. Okay, so it's a product of two functions. Now, product rule. So derivative of 2x, that will be 2 times y cubed. So that's f prime g plus f, which is 2x times g prime. G is y cubed. So then g prime, of course, y is a constant, y cubed is a constant, then derivative of constant is 0. So that's 2x times 0. So that will be 2y cubed. So the second derivative of f with respect to x is equal to 2y cubed. Okay. Of course, you can do, for example, I don't know, let's say you want to compute f of xy or fyx, fxy. Okay. Or fyx, let's say. Okay, so derivative of f, so this is derivative of f with respect to x and then with respect to y. So we need to derive derivative of f with respect to x. We need to derive fx with respect to y, right? So here again, first derivative with respect to x, and then you derive with respect to y. So, so what's the derivative? So we need to derive fx. So derivative of f with respect to x is 2xy cubed. So we need to derive 2x y cubed with respect to y. Right. So now, so then fxy here, that will be equal to, again, this is a product multiplication, so it's a product rule, so we have 2x times y cubed, but now you need to be careful, this is with respect to y, right? So with respect to y, it means that x is a constant, so 2x y cubed, so f prime, so this is my f, this is my g, so f prime, derivative of 2x, but x is a constant, so then derivative of 2x, 2 times a constant is a constant, so derivative of 2x is 0, so 0 times y cubed, plus f, which is 2x times g, the derivative of g prime. But g is y cubed. So what's the derivative of y cubed? Y here is not a constant, it's a variable. So derivative of y cubed would be, it's like derivative of x cubed. Derivative of x cubed is 3x squared. So derivative of y cubed is 3y squared. Okay, so then fxy would be equal to, so this is 0, and this is 6xy squared. Anyway, guys, etc., etc. So anyway, I guess in the homework I will give you a couple of derivatives to compute, so then you can have a chance to to practice. Okay, what else I'm gonna say? So let's do the examples here. More examples. So let's say f of xy is equal to x cubed y minus x y cubed over x squared plus y squared if xy different from 0, 0. Oops. Different from 0, 0. And then 0 if xy is equal to the origin, if xy is 0, 0. Okay. Let's say first, let's find f of x at the point 0, or partial derivative of f with respect to x at the point 0, 0. Okay. So what's this function f? F is given by this rational function here, x cubed y minus x y cubed, etc. if the xy different from 0, 0. And it's equal to 0 if xy is equal to 0, 0. So what's the derivative of f with respect to x at the point 0, 0? So here, guys, you need to, again, you need to understand that the derivative at a point, it's not about the value of the function at the point, but it's about the values of the function in the neighborhood of the point. So this, we cannot just, here, it's not because f of xy, f of 0, 0, so here, what I'm saying is f of 0, 0 is 0, right? So it's not because f of 0, 0 is 0, then you can just take, derivative of 0, and you say, well, derivative of 0 is 0, so then this partial derivative of f with respect to 0 at 0, 0 would be 0. That's not true. You cannot just derive the value of the function at the point. That's not, it's not possible here. So we need to use the limit definition here because, again, the value of the derivative of a function at the point, it's not just, it's the change of rate. I mean, it's about the behavior of the values of the function in the neighborhood of the point, not just at the point. So we need to use the limit definition here. So then partial f, partial x at the point 0, 0. Remember, by definition, that was limit h goes to 0. So here, like, this is a 0, 0. This is like my AB in the definition, limit definition. So a is 0, b is 0. So this is the limit h goes to 0 of f. So here, x with respect to x. So y is a constant, so y is fixed. So y is equal to 0, so it's fixed. So we vary x here, so we vary 0. So that's f of 0 plus h, f of a plus h, 0 minus f of 0, 0, f of ab. Right, this is, again, this is a plus h, this is b, this is f of ab over h. So then that will be equal to, so this is limit h goes to 0, f of 0 plus h, of course, is f of h0 minus f of 0, 0 over h. Okay. Here, guys, f of h0. So what's f of h0 here? So you need to be careful. H approaches 0. It doesn't mean it doesn't mean that h is equal to 0. It means that h is close to 0. So here, to compute f of h0, so f of h0, so x is h and y is 0. So we need to replace here this x by h, so here x by h and y by 0. So I need to replace this x here by h and y by 0. Okay, so that will be h cubed so h cubed times 0 plus or minus, sorry, minus x which is a, so it's minus h times y cubed. Y is 0, so that's 0 cubed, over x squared, which is h squared plus y squared plus 0 squared. So that would be equal to, sorry, I forgot the limit here. So here is supposed to be equal limit h goes to 0. So, sorry, it's not limits, that's f of h0. So that's equal to, so that's f of h0 is equal to what? So this is 0 over h squared. So that's equal to 0. Okay. Now what's f of 0, 0? Well, f of 0, 0, it's just here x, y is equal to 0, 0, then f of 0, 0 is 0. So it's just 0. Okay, so then I can compute now my partial derivative of f with respect to x at 0, 0. So then, so here's the answer. So partial f, partial x at the point 0, 0. So we said it's the limit h goes to 0, f of h 0 minus f of 0, 0 over h. F of h0, we said it's 0, minus f of 0, 0, we said it's 0 over h, so it's just 0 over h. So then partial f, partial x 0, 0 is equal, so this is 0 over h, so it's equal to 0. So this is equal to 0. We can do the same thing for the partial derivative of f with respect to y at 0, 0, but then that will be, so partial f, if you want to find, let's say, partial f, partial y at 0, 0, so that will be the limit h goes to 0 of f of 0 h plus 0, 0 plus h, sorry. So here it's 0 plus h minus f of 0, 0 over h. Okay, same thing. Now, question is, so the question is, the partial derivative continuous at 0, 0? Remember, a function is continuous if the limit when you approach the point of the function is equal to the value of the function at that point. So f of x is continuous at the point 0, 0 if limit of xy approaching the point, which is 0, 0, of f of partial derivative of, so my function here, I'm talking about the partial derivative of f with respect to x. So I'm interested in the partial derivative of f with respect to x. That's my function. So I'm interested in the limit of partial derivative of f with respect to x when xy approach the origin. So if this limit here is equal to the value of the partial derivative of f with respect to x at 0, 0, which is by the what we just did, it's equal to 0. Okay, so here, guys, we need to compute the limit. So we need to compute the limit of the partial derivative of f with respect to x when xy approach 0, 0, right? So now the question is here. So here, you need to be careful. This is, so here xy approach the origin. Again, it doesn't mean that xy is equal to 0, 0. It means that xy is close to 0, 0. Okay, and if xy is close to 0, 0, what's the value of partial f, partial x? So what's this partial f, partial x? So this is the derivative of f with respect to x for x. So this is, so the derivative of f with respect to x for xy different from 0, 0. Again, it's xy, they're supposed to be close to 0, 0. They're not equal to the origin. They're not equal to 0, 0. They're close to the origin. So x, y are different actually from 0, 0. So what's f derivative of f with respect to x for x, y different from 0, 0? Well, then we need to compute this is my function f when x, y are different from 0, 0. So now I can use this to compute the derivative of f. So to compute the derivative of f with respect to x for x, y different from 0, 0. So what I'm saying here is for x, y approaching 0, 0, so we need to use x cubed y minus xy cubed over x squared plus y squared to compute partial f partial x. Okay, so what will be partial f partial x in this case? Okay, so what's the derivative of f here with respect to x? So here again, y is a constant. So this is a fraction, right? So we need to use a quotient rule. Oops. So quotient rule. Okay, so the top would be the f and the bottom would be g. So let's use the quotient rule here. So f, so that would be quotient rule, right? So that will be f prime g minus f g prime over g squared. So what's f prime? So derivative with respect to x, again, y is a constant. So for example, so here, so I'm going to use the quotient rule. So it will be like f prime g minus f g prime over g squared, right? So that will be, so derivative of the top f, so derivative of f with respect to x, y is a constant, so we have x cubed, for example, y, so that will be 3x squared times y, and then plus 0, because, y is a constant, I'm supposed to apply product rule for just this term, minus, again here, this term here, product rule, derivative of x is 1, derivative of y cubed would be 0 because y is a constant, so it's applying the product rule, so it would be 1 times y cubed, so it's y cubed plus 0, so it's going to be just y cubed times, x squared plus y squared, okay, minus, and then f, which is the x cubed y minus xy cubed. Now, derivative of the bottom, derivative of x squared, that will be 2x, plus derivative of y squared, y is a constant, so y squared is constant, so it's just plus 0, so it's just 2x over, of course, x squared plus y squared, so g squared, so squared, okay. So we need to compute the limit xy going to 0 of f of x. Of course, here that will be just everything is x is 0, y is 0, so it's going to be 0 over 0, so indeterminate. So we need to use, to find this limit, actually we need to use the polar coordinates. So my x is r cosine of theta and y is r sine of theta. Okay, so let's compute this. Let's do this. So that will be limit. So xy approaching 0 at the origin means the radius is approaching 0. So that's limit r going to 0 of. So you need to replace x by r cosine and y by r sine. Here you can see so let's see here. So you just replace x by r cosine and y by r sine. So for example here, x squared plus y squared, you know, if you do x squared plus y squared, that will be r cosine theta squared plus r sine theta squared. So you can just, you know, you can factor out, that will be r squared, so you can factor out r squared, that will be cosine squared plus sine squared, that will be 1, so that's r squared times 1, so that will be r squared. So this thing here, for example, that will be r squared. Here in the bottom, this is r squared squared, right? So that will be r to the 4. So anyway, what I'm saying, guys, is that, so you have r going to 0, so we have 3x squared y, so that's 3 so 3x squared, so that's r cosine theta squared. Sorry, here. So 3r cosine theta squared times y, so times r sine theta minus y cubed, which is r sine theta cube, so minus r cube sine of theta cube. So this whole thing here times r squared, so times this r squared here, minus, and then I don't have enough space, so this x cubed y minus xy cubed. But anyway, the thing is, what's really important here is the powers of r. So here is going to be like r to the 4. So here is going to be like, you know, like minus, so parentheses here, r cubed cosine cube theta minus etc. And then we're going to have what, 2x. Sorry, it's x cubed times y. So it's here, we're gonna have cosine theta cube times r sine, times r sine, minus, and then minus what? So we have xy cubed now, so it's minus r cosine r cubed sine of theta cube times, and then 2x, so it's times 2r cosine of theta. And then the whole thing here divided by r to the 4th. Okay. But anyway, so there will be limit r goes to 0. So you see, guys, here in the top, we can factor out, so you see here, you have, so here you have this r squared times r, so that's r cubed, and there's r squared outside, so that's r to the power 5, so that's r to the 5th, so that's r to the 5th. Here the same thing, there's this r cube here, right? This r cubed times this r squared, so that's r to the 5th. Here is the same thing, here they have r cubed times r, so that's r to the 4th, but then there's this r here, so that'll be r to the 5th. Okay, and same here, r times r cubed, that's r to the 4th times r, that'll be r to the 5th. So basically you have r to the 5th in the top, we can factor out r to the 5th in the top times wherever, okay, some stuff here, okay, over r to the 4th. But then the thing is, you see here r to the 5th over r to the 4th, so r to the 4th cancel out, so this is, it's just equal to limit r goes to 0 of r times some stuff, and 0 times wherever, it's just 0. So this limit here is equal to 0. So what I'm saying here, guys, is that limit when xy goes to 0 to the origin of f of derivative of f with respect to x is limit, so r goes to 0 of the derivative of f with respect to x is equal to 0. And that's exactly derivative of f with respect to x at the point 0, 0, right? That's what we computed in the first the first part of the problem, right? Here. So we said partial f partial x at 0, 0 is 0. So that's exactly, so this 0 here is exactly equal to the value of the partial derivative of f with respect to x at 0, 0. So the answer to the question, yes. So partial f partial x is continuous at 0, 0 because the limit xy going to 0 of partial f partial x is equal to partial f partial x at the point 0, 0. Okay, so yes, it's continuous. If you get a different value, if this limit here is different from this value here, okay, then partial f partial x wouldn't be continuous. It's not continuous at 0, 0 if you get two different values. But here the two values are the same, both are equal to 0. So then f partial x is continuous at 0, 0. And actually, this is part of definition. If the partial derivatives, so if the partial derivatives are continuous, exist, if the partial derivatives exist, so sometimes of course they do not exist. I mean, if the limit is not if the limit do not exist, you know, then the partial derivative do not exist, of course. But if the partial derivative exists and continues at AB, then we say that f is differentiable at AB. Then f is differentiable at AB. Okay. Let me just remark another thing here, guys. Sometimes you can have a function f which is not continuous at a point, but still the partial derivatives exist. Okay, so this is kind of different from like the case of a function of single variable, you know. I mean, the derivative would exist if a function, but the necessary condition is that the function is continuous at the need to be continuous at the point, right? But here, sometimes you can have functions that are not continuous at the point, but still the partial derivatives exist. So let's do an example here. Let's say here's an example. Let's say f of xy is equal to, let's say, 2xy over x squared plus y squared if, again, xy different from 0, 0. Different from 0, 0, and 0 if xy is equal to 0, 0. Okay. Well, here first f, you can see that f is not continuous at 0, 0. Okay, why? So first, let's compute f of 0, 0, of course, is equal to 0, right? But then, what's the limit when x, y approach 0, the origin of f? So that should be, again here, x, y approaching 0, it means that x and y are different from 0. They are not equal to 0. So that's my function f is the 2xy over x squared plus y squared. So that's the limit x, y approaching 0, 0 of 2xy over x squared plus y squared. Okay, and you can use, for example, here polar coordinates, and you can see, so that's limit r goes to 0, so that's 2 r cosine r sine over, so r squared, again, cosine squared plus r squared sine squared. You can factor out r squared, so r squared times 1, so it'll be r squared here. So then here you have r, this is r squared, so that's r squared over r squared, so r squared cancel out, right? This cancel out, so that will be equal to limit r goes to 0 of 2 cosine theta sine theta. Okay, so this limit here depends on the angle theta. So for different thetas you get different limits. So then here the limit actually do not exist, depends on theta. So here the limit do not exist because it depends on theta. Okay. And so f, this is different from, so this limit here, of course, this is different from f of 0, 0. So then limit x, y of f, this is not equal to f of 0, 0. Okay, which is f of 0, 0, 0, right? So because again, this limit here depends on theta, right? For each value of theta, you get a different number, right? So, so it depends on theta. So then f is not, so here x, y, limit of f, x, y going to 0 is not equal to f of 0, 0. So f is not continuous at 0, 0. Okay. However, the partial derivatives exist. For example, partial derivative of f with respect to x and partial derivative of f with respect to y at 0, 0 both exist. Okay, so because, well, we can compute. Let's compute. So what's partial f, partial x at 0, 0? So by definition, that's the limit. H goes to 0 of f. So here x, y is a constant. So it's 0 plus h. So it's h 0 minus f of 0, 0 over h. So what's f of h 0? Just replace, x by h and y. Here you can just replace this x here by h and y by 0. So that will be a 2h0, that's 0 over h squared, so it's just 0. So this is just 0 minus 0 over h, so that's 0 over h, so that's 0. So yes, partial f with respect to x, partial derivative of f with respect to x at the point 0, 0 exists. It's actually equal to 0, so it exists. And the same thing for partial f, partial y. It also exists. So you see here, this is an example where f is not continuous at the point. However, the partial derivatives exist. Okay, so it's not the case of single variable. I mean, if the derivative, in order for the derivative to exist, you need f to in order for the derivative to exist at a point for a single variable, you need at least the function f to exist. You need the function f to be continuous at that point. Here, it's not the case for several variables. F is not continuous. This is an example where f is not continuous at the point. However, the partial derivatives exist. Okay. Anyway, guys, you can find, I guess, more details and examples in my lecture notes. So I'm gonna stop here, and I will see you next time. And if you have any question, again, just email me. Thank you. See you next time.